Okay, okay. So, sorry about the delay. Any questions about anything? Yes.
Is this the time to ask about the prelim stuff, or
Let's do a little bit of stuff up and then we'll take the break, and starting with and after the break, we'll talk about any Q&A you have about anything prelim related. But any other questions people want to ask? Yes.
Is the current plan for online learning to do not live lectures or live?
Okay. Here's the story. Like, I'm thinking that I will come in here and at the usual, just because I'm used to the time, and just give lectures and tape them and then upload them manually to YouTube. So no matter what time zone you're in, I'm not going to be trying to zoom these out, because there's no way that Cornell's Zoom capacity is going to handle synchronous lectures for anybody who wants to do that. It's a crazy idea. Let me just say, as an aside, I won't even turn the camera off, but with all due respect to my well-paid colleagues in Day Hall, okay, the devil is in the details, okay, and you didn't think it through, okay. Not only the live or the whatever you called it, online learning. I mean, but what about kids who, live halfway around the world, okay, who already had their plane tickets and now they have to buy new ones, or they can't go home right now? Or what about kids for whom school is a refuge and home sucks, right? You don't want to go there, right?
That's most people. Most kids without internet access at home. There's quite a few. I think my earlier class, like 12% said we don't have.
Yeah, so that hasn't, all these things are important, and I just don't think, I think that this business about go home to mom and dad for spring break and stay there, is based on a kind of an old-fashioned model of college kid, okay? And the modern college kid is much more nonlinear and less time invariant and whatever else. Okay. Second of all, it's kind of like, I can't imagine what it looks like to you guys, but this is how it looks to us. It looks to us like, okay, we're going to send the kids home. You figure out how to give your courses, And so if Bruce Land, say, were giving his microcontrollers course this semester, there'd be no way. And meanwhile, like folks who are giving total lab courses, like Joe Scavir is giving this embedded OS course, there's no way the students are going to be able to do anything because, they need to be in there. You?
No, so we're still doing groups. We're just taking a larger lab kit home with us. So we can essentially work and program the board anywhere. So
yeah, okay. Well, good. I'm glad Joe has come up with a creative solution. See, for theory courses, I see a path forward. I see how we can do this. I haven't figured out everything yet, but I think we can do this. And I think you'll probably get just about as much out of the course as you would have gotten, except for spending time with me in person and each other. I mean, I feel bad because I'm just getting to know you guys, and then I have to say bye. And I'm just praying you'll sign up for 3250 next fall so I can re-meet you. But anyway, so my plan, is going forward is to give lectures in here and record them and upload them, and so I thought to myself, some kids will stay around. I know that. I mean, I know there's a way to petition, like if you're totally screwed by this, you can quote unquote petition. And I don't know who's going to look at the 14,500 petitions that are going to be submitted. Bryce, you have a question? No, you're just doing this?
But I mean, I do have a question, but you can finish.
Yeah, okay. So, reject call. California area code. Okay. Anyway, there are people who are going to stay around. Like, if you live, say, in Eddy Gate or anywhere else in College Town, the university can't tell you, no, you can't come back to your apartment. We're going to send out the cops. That's not going to happen. So there will be people around. I know, there will be people around. So I'm thinking, well, I'm going to come in here Tuesday, Thursday, 11:40, and give this lecture to a nominally empty room. But the ones who are around, maybe some of you are still around, you ought to be allowed to come and show up, right? So I sent an email to the dean of the faculty and the associate dean last night saying, hey, what about kids who stay around? They're welcome to come, right? And I really haven't heard back. I did hear one reply. Okay, Danu, I'll get to you in a second. I heard one, or no, yeah.
I am not done yet.
You're not Danu. You wait, Danu is around here somewhere. Yes. I'm sorry, confusion. All right. Tell me your name.
Esther.
Esther. Okay, I met you one time before. So what was you were going to say something?
Oh, we just heard that the buildings themselves were closed after spring break. Like Phillips, Day, whatever.
For
Duffield,
undergraduates, undergraduates won't have access.
So they're going to post police at the doors.
No, like the card access.
Oh, the doors will just be locked.
Yeah.
You could just hang by the door.
Yeah, I mean, but the point is that to me, I haven't heard, you know,
We're not trench
but
coat.
so the one reply I heard was the following, like, are you talking about people who went home for spring break or not? The ones who stayed here or the ones who went home for spring break and came back? And I said, well, there's no way for me to know whether what they did over spring break if they live off campus. So I have no clue how this is going to go forward. Now, you say the buildings are going to be locked,
Yeah.
Esther? Did you hear that?
They're trying to make it so that everyone
Not
comes
yet.
and stays
We really
alive.
don't want people to be.
They're
Mike
like
Thompson
trying.
confirmed yesterday they're doing everything they can to keep undergraduates as far away from Ithaca as possible.
Yeah.
Okay.
They're going to lock all the buildings, and they want even undergraduate researchers to go. Although I've heard multiple defense who say they're going to try to finagle their students back into the buildings.
I mean, I feel like resisting this, to tell you the truth, but I don't know what's going to happen, honestly, about the.
How they're going to lock Duffield Atrium. I don't think those doors have locks.
Also, the Phillips Hall loading dock is unlocked every single day.
Yeah.
9 to 5 with no card access. So
Right.
unless someone finally fixes that,
Can you cut that out of the video?
Yeah, and here we have this whole, like, you know, you or someone close to you has paid a lot of money for this education, and if they're sending you home and saying, figure out a way to get the most out of your classes, and your professors will do the same, you know, I think that merits a refund of some kind, you know, to tell you the truth, honestly. So I don't know. Yeah, Brace.
Like some of us like applied to like I'm affiliated with ECE this semester.
Yes.
Will like the advisors still be assigned?
Yeah, but you know, like, yeah.
Like will we still be able to like I don't know like conference with them?
Yeah, well, yeah, I'm going to tell everyone, like, pre-registration is coming up at some point. So,
After spring break.
no, but that's a busy,
It's like a week after or something.
that's a busy time of year for me as the EC advising coordinator, answering a lot of questions and stuff. So I plan to be as available as I can, you know, email, Zoom, whatever, you know, like whatever it takes. We'll keep that up. But yeah, I mean, I don't know how every individual advisor is going to handle things, and I will still assign advisors. If you're still assigned to me, consult me, you know, because a lot of you are still assigned to me online, even if you're going to be assigned to someone else at some point. But anyway, we'll figure it out. We'll do the best we can with the hand we've been dealt. That's the way I look at it. Okay, now Alex is going to have to remind me to do what I have to do. Like if I finish this board, I should, yeah.
Make sure you turn the face the other way.
Let me just see how this looks. Bad hair day. Well, what else is new? Anyway, okay. So, I want to talk just for, you know, a half an hour or so just to introduce you to this. We essentially finished the chapter 5 stuff. The general FIR/LTI system stuff. And the key things, you know, the key takeaways from that, we had this idea of what is an LTI system, what is the impulse response of an LTI system, what is the impulse response in special cases FIR. And the key picture was always that the impulse response is not only the response to an impulse, but it's also what you convolve with inputs to give you outputs. So it plays this dual role. And that was the big message there. And you learned a little bit about convolution as an operation between discrete time signals. So what I want to do now is we're going to move on to chapter 6 stuff. And this is all about putting the system stuff together with the sinusoid stuff that we've talked about before. So essentially, what this is going to do is it mates the kind of sinusoid spectral, etc. stuff with the system stuff. So really what we did, if you want to think in general terms about what we've done so far, is we spent a while talking about signals, a special class of signals, how to model them, how to represent them schematically, spectrally, etc. Then we spent a little while talking about systems, special kinds of systems, FIR, and more generally LTI systems, impulse response, all that. Now we're going to talk about driving these systems with these special signals and see what comes out. Okay? So suppose I have a causal FIR system governed by a difference equation that looks like this. Y of n is equal to the sum from k equals 0 to m. Is that what we've been doing? bk. It's amazing how, like, when you have all this weird stuff, new stuff to think about, you forget. Your mind doesn't work as well. You lose sleep. You guys have probably noticed that over the last few days. So I went into my lecture yesterday, my other class, and I was like, okay, now I have to remember what what we're talking about. So that's sort of how I felt today coming in here. But I think this is going to be good for me and good for us to actually play around with these things. Okay, so you have this causal FIR system governed by this. Suppose we drive it with a sinusoid. Okay, so suppose, and I'm checking the laptop. This is still covering this board, I think. But let me just make absolutely sure I got the whole thing. Okay. Suppose we drive the system with one of our old friends, say x of n equals a cosine of n omega 0 hat plus phi. So this is a discrete time sinusoid. And we know how to graph the spectra of these things, and we know, like that the discrete time alias frequencies, blah, 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 different role from continuous time. We talked a lot about that. What happens? The output is this. It's just the sum from k equals 0 to m of bk, x of n minus k. So it's going to be bk a cosine of, and everywhere you see an n, you have to put an n minus k. So cosine of n minus k, omega 0 hat plus phi. All right. And so what is that? That is an expression for y of n as the sum, and let's even write it in a slightly different way so it becomes really obvious what I say. bka cosine of n omega 0 hat plus, and now let's put in parentheses, minus k omega 0 hat plus phi. All right. Now each of those terms in the sum is a discrete time sinusoid with normalized frequency omega 0 hat. So each term in the sum so far so good, eh? I'm not getting this right. Let's see. I want to see if I can. I think I got that. All right. So each term in the sum is a discrete time sinusoid of normalized frequency omega 0 hat. And you may remember that when we had continuous time sinusoids, so this is the same for every term, same frequency for every term. You may remember that when we had a sum of continuous time sinusoids of common frequency f0, we could always express that as a single sinusoid of frequency f0. So recall that if I take the sum of a bunch of continuous time sinusoids of the same frequency, f0, I can write that as a single sinusoid of frequency f0. And how do we do that? Phasor amplitudes. So the key was phasor amplitudes of the individual terms. You take the phasor amplitudes of the individual terms, add them together. The result of that is the phasor amplitude of the sum. And that's how you do that. So we can do this in discrete time as well. All right, so let's see. Okay. I'm so not used to this. Yeah, this is going to be really oblique, facing that. I might have to confine the lectures to the middle two boards, but that's okay. All right. Let's make sure. Sorry, guys. All right. So the key is phasor amplitude. So the same trick works here. Let's look at the kth term in our sum. What is that? That's bk a cosine of n omega 0 hat plus minus k omega 0 hat plus phi. That's the kth term in our sum. I can write that as the real part of bka times e to the j, whatever's in here, n omega 0 hat plus minus k omega 0 hat plus phi. And that, in turn, is, if I factor the e to the j omega 0 and omega 0 hat out of that, that is this, bka e to the minus k omega 0 hat plus phi times e to the j and omega 0 hat. And this thing in the parentheses is the phasor amplitude of the kth term. There's a j missing, sorry. So it's e to the j minus k omega 0 hat plus phi times all that times e to the j n omega 0 hat. This term in parentheses is the phasor amplitude of the kth term. And when we add all the terms together, real part distributes over addition, just as in continuous time. And we get this for y of n. So thus, y of n is going to be equal to, thank you. Maybe one of the pirate students who stays around can be moving my computer, moving the thing around for me, something like that. You know, actually, there's a grad student who's been sitting in on this class. He might still be around. He might still have card access to the buildings. Oh, my God. Anyway, y of n is going to be this. If you sum all the terms together, you're going to get the real part of the sum of all those phasor amplitudes times e to the j n omega 0 hat. What is the sum of all those phasor amplitudes? It's this. It's the sum from k equals 0 to m of the parenthesized terms there, bka e to the j times minus k omega 0 hat plus phi. So this is the phasor amplitude of y of n. and we're going to give it a name. We're going to give it a name. Notice it's a function of omega 0 hat. Depending on what the frequency of x of n is, this is going to be different. So let's call this h hat of omega 0 hat. And I want to caution you, here's another place. Can you see me? No. Here's another place where the book and I disagree on notation. The book calls this, so this is not the same as book, and there's a reason that I use this notation that I'll explain later on in the class, but I'm not going to give that diatribe now. I'm going to give it to an empty room and hope you watch at home. And by the way, while giving these empty room lectures, I'm going to try to look at, call everyone out at least once, like say hi to people, like whatever. So I get to learn your names from your pictures if I can recognize you, right? And if you're someone who doesn't show up, I might say, oh, hey, oh, Cameron, you don't usually come to class, I've only seen, like that kind of thing. And Hermogenes, and I won't exit 114 guy over there, And anyway, I'll try to call you all out at some point. And just so, yeah, even the CS majors. Not the same notation as the book. The book calls this something that I find really ugly, and it only applies in certain cases, so caution here. And you may say, well, there's too many hats going on. Well, in my world, yes, Bryce.
What's the notation of the book?
OK, I'll see if I can. It burns, but it's this, h of g to the j omega 0 hat. That's what the book calls it.
Oh, so you just don't need the e to the j.
Well, and I have a hat on the h. See, in my my notational panacea world, I don't have omega hat as discrete time normalized frequency. I just have little omega. And I have big omega for continuous time frequency, or the other way around. I don't have any hats on the frequency. And I put a hat on the frequency response. OK. But anyway, that's what the book calls it for now. OK. So yes?
Are you saying h omega hat is the summation term, or is it the whole thing?
It's this whole phasor amplitude. Let me write it out. So h hat of omega 0 hat is equal to the sum from k equals. Actually, wait. The a is not included in h hat of omega hat. So just the a, though. And I apologize for this, folks. I'm going to revise this board. So this is the same as the real part of, this is going to be the term in parentheses, sum from k equals 0 to m, bk e to the minus e to the j, e to the minus jk omega 0 hat, that thing, times a e to the j n omega 0 hat plus phi. OK. This is what I'm going to call h hat of omega 0 hat. And again, this caution still holds. Caution, this is not the same as the book. Notation for this. This is the term I'm going to call h hat of omega 0 hat. So it's equal to this. It's sum from k equals 0 to m. Glad you asked me that question, or I wouldn't have found that mistake. Thank you. Bk e to the minus jk omega 0 hat. OK, now what's interesting about this h hat of omega 0 hat? What this says is, this says that, so this enables us to express y of n as this. It's also going to be a pure sinusoid with some amplitude, same frequency, same normalized frequency as x of n, and some phase. What is this A prime going to be? A prime is going to be the magnitude of whatever it is multiplying e to the j n omega 0 hat here. So it's going to be the magnitude of sum from k equals 0 to m bk e to the minus j k omega 0 hat times a e to the j phi. And that's just going to be the magnitude of h hat of omega 0 hat times a, which was the amplitude of the x. And this is because the e to the j phi, that always has magnitude 1. A is a positive real number, so that just slips right out of the magnitude sign, and we're left with that. And the phase phi prime of the output y of n is just going to be the phase of the input plus something. It's going to be phi plus the phase of h hat of omega 0 hat. Camera? Oh, this is going to be a disaster. Can folks in the front row see over this computer? OK, good. This doesn't react as well as it should to rotation.
Get a small lazy Susan.
Yeah.
So I had the idea for ECE 5725 to make a Raspberry Pi based camera that follows the professor around.
Yeah.
But unfortunately, that's not finished yet.
It's not finished yet. Yeah, well, that would be better than any lecture capture technology available at Cornell now. And also here, by the way, Day Hall colleagues, when you got rid of VideoNote, you made life very difficult for some of us faculty members in CS and ECE. Admittedly, we're the only departments that ever used it. But anyway. I could zoom the board to my laptop.
Yeah, and you'll be doing exactly what they all want.
Well,
That sounds like giving Dayhall satisfaction.
Yeah.
in the faculty senate meeting yesterday, though, I got up to ask the question about students who like live halfway around the world and don't want to go home. Okay, and one of my colleagues from Natural Resources got up and whispered in my ear. He's an expert in IT. He said, while you have the microphone, tell them that I talked to an IT person and they said there's just no way that Cornell Zoom is going to be able to handle, the load. And so I got to say that, but I attributed it to him.
I used Zoom before to barely handle like 7 people.
Yeah.
600-person lectures.
Yeah. Well, we'll see what. See, the cool thing about Zoom is that I can do this like at home, right? I can do Zoom at home, and you can see like what my house looks like, and right.
Do you think they'll let me stay here? I'm just really in the quarantine zone. Like, the show is right next to the quarantine.
That makes sense.
I feel like I should just not go.
All right. Let's simmer down. Alec, you have a question?
It's just about how you can capture everything.
Okay. Well, by the way, in case you didn't read your email, I set up a discussion thing on Canvas, and I've never used a discussion on Canvas before, for you to put up suggestions for how to move forward and anything about like how lecture capture. What are you telling me something or not? Okay.
Just conducting the air.
Fair. So yeah, that's a musical thing that you're doing, right? Yeah. Okay. Yeah. Any suggestions you have for making life easier for all of us? That would be awesome. Or vent. That's cool too. Vent on there, because then I can vent back. Okay. All right. So let's have a look at this. Let's make sure we buy this. Yes.
Why does the sign of BK not matter?
It does. It does, because it comes in when you're figuring out the magnitude and phase of this number here. Like if the b's were negative, yeah. All right. Bottom line, y of n. If you put a cosine x of n equals a cosine n omega 0 hat plus phi into the system, then what comes out is another one. Whose frequency is the same and whose amplitude and phase are possibly different. And how do they differ? They differ according to these formulas here. And just to make sure you buy the formula, if y of n is equal to that thing times a times e to the j n omega 0 hat plus phi, that means the phasor amplitude of yn is that thing times a times e to the j phi. So the amplitude of y of n is the magnitude of that phasor amplitude, which is this thing, which is that. And the phase of this thing is the phase here plus the phase of this. OK, so that's the key thing. And terminology, we call h hat of omega 0 hat the value of the system's frequency response at frequency omega 0 hat. And what is just the plain frequency response or frequency response function of the system? That's the thing we get when we allow omega hat to vary over frequencies. So if you think of allowing omega 0 hat to quote unquote vary over omega hat space, you get a function of omega hat, namely h hat of omega hat equals the sum from k equals 0 to m bk e to the minus jk omega hat. This is called just the plain old frequency response of the system or frequency response function of the system. So this function is the frequency response, or if you will, the frequency response function of the system. And what it tells you for sure is how the system responds to pure sinusoids. And it's going to turn out to tell us even more than that, as we'll see in a bit. OK, so note h hat of omega hat is, in general, a complex valued function, a complex valued function of omega hat. Only in rare circumstances is it not complex valued. It's going to have some symmetry properties. We're going to get to that as we go along. So more later on its properties. It's going to turn out, for example, to completely determine the system's impulse response. So you can figure out the impulse response from this, just as you can figure out this from the impulse response. Therefore, this tells you everything about the system. That's going to turn out to be true. It's going to turn out to be conjugate symmetric in omega hat. It's going to turn out to be 2 pi periodic function of omega hat. We'll get to those properties as we go along. But for now, note that h hat of omega hat tells us the whole story about how the system responds to pure sinusoids. So it tells us all about how the system responds to pure sinusoids. Of various frequencies. So, for example, suppose, say, omega 0 hat is such that the value of h hat of omega 0 hat is 0. That could happen, right? What happens then when I put any cosine of frequency omega 0 hat, so a cosine n omega 0 hat plus phi. When I put that into the system, what comes out? What comes out is a y of n with some amplitude a prime, some phase phi prime, same frequency omega 0 hat, where the amplitude a prime is given by this formula, phase is given by this formula. So who said 0? Critique? Yes, the 0 signal. So if I put x of n equal to this into the system, then I get y of n is equal to the 0 signal. In other words, the system annihilates pure sinusoids of frequency omega 0 hat when h hat of omega 0 hat is 0. And in a less extreme case, like suppose h hat of omega 0 hat is small, then it attenuates cosines of that frequency. If h hat of omega 0 is large, it amplifies sinusoids of that frequency. So in some sense, this exhibits the filtration properties, whatever. We'll get more into that later on as we talk about filters and stuff. So a sort of a softer version of this, a kinder, gentler version, is that h hat of omega 0 hat small, that corresponds to the system attenuating, maybe not annihilating, but attenuating sinusoids of frequency omega 0 hat. And h hat of omega 0 hat large is going to correspond with the system amplifying those. OK. So this is our first taste of frequency response. And that is where I'll stop for today before the 3-minute break. And then we'll spend the rest of the time, if you have any questions you want to ask about stuff. We can take the break and then ask questions, or you can just start firing away now. Or not. Like, yeah.
Question about this, how could h have a phase?
How could h have a phase? Well, if it's a complex number, right? Like h hat of omega 0 hat, good question, is this. It's the sum from k equals 0 to m of bk e to the minus jk omega 0 hat. So let's look at a specific example. OK, so suppose, say, b0 is equal to 1, b1 equals minus 1, something like that. OK, then what is h hat of omega 0 hat? It's going to be 1 minus e to the minus j omega 0 hat. Right? That's a complex number. We can play with that. Let's do that, because this is kind of cool, right? This is the same as e to the positive j omega 0 hat over 2 minus e to the minus j omega 0 hat over 2 times e to the minus j omega 0 hat over 2. We're going to see this later on in the semester, by the way. This is 2j sine of omega 0 hat over 2 times e to the minus j omega 0 hat over 2. So you can see right away that the phase of this thing is going to be omega 0 hat over 2 plus pi over 2 plus maybe a pi if this thing is negative. So this will have a phase. A non-zero phase. Because it's a complex number. Okay, now I'm not sure. I guess I should follow things around with this question time as well. So you can catch your breath. Oh, by the way, Luke one of our TAs brought the homework 2s, the graded homework 2s, as a peace offering. Okay, from your friendly TAs who have had a little trouble getting organized on the office hours. Sorry about that. We're going to figure out how to, we're going to meet tomorrow. TAs and I are going to meet tomorrow and talk about, if, how, whatever they're going to virtualize office hours for you guys going forward. But anyway, here's the thing. I'm not going to stand up here and do a review session today, but if you have questions, feel free to ask them. Any kind of question you want to ask at all, prelim or otherwise. And if you want to leave, if you'd rather just go off and socially distance yourself and study, that's fine. I won't be offended if you get up and walk out in a huff, whatever, or not in a huff. But if you want to stay and talk, ask questions, that's fine. So I'm all ears. Yes?
Can you give an example of a signal that samples to a discrete time sinusoid that isn't actually a sinusoid?
Okay, this is a question. He asks the following awesome question. And maybe one of you can answer this. I have one answer in mind already. What's an example of a continuous time signal x of t that samples at some rate or other to a discrete time sinusoid x of n, but x of t itself is not a continuous time sinusoid? Bryce.
The sinusoid posed in question 3 on the prelim that you posted.
The sinusoid.
Or the input signal, because it wasn't periodic.
Right.
But when you sampled it, it did gain a fundamental frequency. Because you had, I believe, there was a frequency at 7 pi in the original one.
Yeah, I remember that problem. There was a problem with that problem, as I recall, last year. But I gave, in the solutions, I gave what it quote unquote should have been. But I want to think of an easier example to answer your question. What's your name, by the way?
Jack.
Okay. Here is an easier example. I'm going to let x of t be a square wave that looks like this. Okay, and I'm going to sample it here, 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 here. And just say this is, how about this being pi over 2? This is time pi, this is time 3 pi over 2, this is time 2 pi, this is time 5 pi over 2, etc. This is x of t, and x of n pi over 2 is equal to cosine of n pi over 2. Okay? So this is a discrete time sinusoid. And this is not a continuous time sinusoid. Fair enough? Okay. Yes?
So I have a question about C to D and then D to C.
Yes.
So say we have an input x of t, and then it comes out as y of t, and y of t must be x print of t with respect to s. So in that middle step, x of n, that according to one of like the multiple choice, that x of n always has to be exactly y of nts. So is that x of n always in the range negative pi to pi because it has to always create x print of y print of t?
Okay, so this question, if I understand it correctly, and Alex, this went dark, so I'm not sure what I'm supposed to do. Yeah, so please, light up again. No,
Again, it did just.
okay, well then this answer to your question, what's your name again?
Maria.
Maria. I met you last year at some point, I think.
I have an older sister. She looks just like me.
And they have the same.
Katerina?
Yeah.
Is that, it's, okay. Okay. All right, so maybe I did meet you. She's a CS major though, right?
No, she's a
ECE? Okay. Ugh, what do I know? What do I know? Okay, so here's the question, as I understand it. You have an ideal D to C, okay, with, say, interpolation interval Ts, right? Out comes y of t, and some discrete time signal x of n is going in here, right? Now, by definition of an interpolator, a T sub s interpolator of any kind, it doesn't have to be an ideal one, y of t interpolates x of n in the sense that y of nts has to equal x of n for all n. Okay? This is because y of t interpolates between the values of x of n. Okay. So that is always going to be true, and that's why whatever that item in that prelim problem was true. Now, the way you phrased your question was, does x of n always have to be omega hat prin or something like that? Yeah. Well, the thing that's difficult about discrete time signals is that it's the same signal when you plug in all the alias frequencies. It's not a different signal that samples the same. It's the same exact signal. So if you came up to me on Ho Plaza and said, is x of n equal to, say, 3 cosine of 0.7 pi plus phi, or is it equal to, say, 3 cosine of 18.7 pi plus phi, and there's an n in there somewhere. If you came up to me and asked that, I would say, it's both. Why? Because the omegas hat here and the omega hat here differ by an integer multiple of 2 pi. Right?
Yeah.
So am I like not answering the omega hat prin part of your question, or?
No, you are. But does the C to D converter do anything special to x of n such that it's always in that range, or can it be they're all equal? So
No, well, the C to D doesn't do anything to x of n. It gives you x of n. Okay, so the C to D, if it samples a high frequency continuous time cosine, okay, then the first way you write x of n might be like this. But then you'll say, well, wait, this is actually the same signal as that. So let's agree always to write discrete time sinusoids with frequencies in between minus pi and pi, period. So yeah, in a way, it gives you that higher frequency discrete time cosine, but that's the same signal as a lower frequency one. Cool. Nick?
Kind of just going off of that, just if we, for the prelim, have to sample a continuous to get to discrete, do you want us to give the omega between, I guess, 0 and pi?
On an exam, I will try to be as explicit as possible in demanding the solution in a certain form if I want to see it in that form. So I'll try to say, my brother-in-law runs restaurants, and he doesn't like the word try. He doesn't like it when someone says, okay, I'll try. You know, he like chews them out. He says, you either do it or you don't do it, right? So I will do the following. If I want the answer, if the TAs and I'll put it that way, want the answer in a certain form, I will be as specific as possible about the form. So express it in the form a cosine n omega 0 hat plus phi with omega 0 hat between 7 pi and 9 pi. I might say something like that. That would be a weird question, but I might say that. Yeah. Okay. Yep.
For like frequencies, finding the spectrum of them, like we use the frequency shift thing.
Mm-hmm.
Usually I think in this class all the questions have been like, there's like the modulating amplitude and then like the sinusoid.
Mm-hmm.
And the sinusoid that's not the modulating thing doesn't have like a phase shift.
Right.
Can you just still use the same like frequency shift rule if that has a phase shift in it?
It's a good question. He asks, like, how does the frequency rule play out when the high frequency thing, the carrier cosine, has a phase? And the answer is, it's a little bit messier, but it works out. I don't remember by heart what the formulas look like, but it's not simply shift the spectrum of the modulator to the right, half the height, shift to the left to half the height. It's not simply that. There's other stuff going on. But yeah, you can work it out. In fact, I thought I gave a homework problem that had a phase in the higher frequency cosine, because I wanted you guys to address that. And what's your name, by the way? Okay. Trying to record names in my head, so when I do lecture to an empty room, I can pretend where you are. Yeah. Some people always sit in the same general zones, you know. So, you know, Jack's always in that. Alex Na is hiding behind him. Hi. Okay. Alexander, another. There's a lot of Alexes. Is the plural of Alex Alices, like indices? So how many Alices do we have? No. Well, there's Alec. Okay. Further questions? Yes.
Can you have a case where you perform the frequency shift operation, but with a product of 3 sinusoids?
You'd have to do it sequentially. His question was, can you do some kind of frequency shift rule if you have a product of, say, 3 cosines? And the way I would do that would be sequentially. I would say, OK, the spectrum of the product of the first 2 I get by taking the spectrum of the first one, shifting it to the right by this, shifting to the left by this, half the height. Now I have a spectrum. And now I have multiplied by another cosine. They say, oh, well, I just take that and shift it to the right, shift to the left, half the height. So heights are going down, shifts are going out, whatever. Bryce.
How much bigger does one cosine need to be than the other in order to do frequency shift?
It's always true, no matter what. Even if you have a lower frequency, even if for some reason you wanted to do the shifting by the lower frequency, you could do that and still get the same answer. Interestingly enough, the math works out. Yeah.
This is kind of a specific question, but one of the questions had x of t is a non-constant periodic signal, and then y of t is x of t squared. I just don't understand how, if y of t is periodic and non-constant, it has fundamental period less than or equal to naught.
OK, so this is from the not practice prelim.
Yeah.
Very, very good notation. I enjoyed that. How about this? How about x of t equals sine of t? So looks like this. And y of t is x of t squared. It looks like this. See that? So this is x of t, has fundamental period this. Y of t has fundamental period half of that.
Okay. I guess I'm confused how non-constant and constant play out here.
How does non-constant play out here? Well, a constant signal has no fundamental period. Every cap t is a period of that. So I wanted to make sure we weren't dealing with a trivial case. And does it say y of t is non-constant as well? If I squared the square wave, that would give me a constant function. the one I gave you earlier.
Yeah, it says if y of t is periodic and non-constant.
Yeah, yeah, okay. Then it'll have a fundamental period. Like if I took the square wave that we were talking about before, or a variation thereof, and I squared that, I just get the constant signal. So that doesn't even have a fundamental period, so it doesn't make sense to talk about it. Yeah.
I have a question about whether, like, when the Nyquist condition isn't satisfied,
Yeah.
fs isn't greater than 2f max,
Mm-hmm.
can we, I know we can't, like, perfectly reconstruct the y of t signal, but do we know anything about the y of t?
Yeah.
Can we say that it's equal to the x of t?
Yeah, yeah, yeah. If you like one of the key results, and this I guarantee you that there was on the not practice prelim, and there will be on this prelim. Instantiations of the following thing: that if I take any cosine, so x of t equals, say, a cosine 2 pi f0 t, continuous time cosine, right? And I put that into an ideal C to D with sampling frequency fs, right? Then take that x of n and put it through an ideal D to C with interpolation interval Ts equals 1 over fs. Then what's going to come out here is x prin, the principal continuous time alias of x of t with respect to, remember, you need that, fs. So this is maybe the most important picture so far in the class. Yeah.
So if our TS for the interpolation is not fs, what do we just kind of?
You have to think about it a little bit. Yeah, yeah. If this TS is not 1 over fs, then let's think about just this part of the picture, x of n going in here. If x of n is equal to, say, and I'll try to get rid of I'll use b cosine of n omega 0 hat plus, say, phi prime. And this is a separate picture. This is a different universe. So this is DC extended universe. This is Marvel cinematic universe. Okay. If x of n is equal to that, okay, and I put that into, so TS equals anything, okay, then when I put this in here into the ideal D to C with interpolation interval TS, I get a signal y of t is equal to b cosine 2 pi f0 t plus or minus phi prime, where f0 comes from figuring out the prin of this. So where 2 pi f0 ts is equal to omega hat prin of x of n. So what I have to do is take this guy and shift it by 2 pi, 2 pi, 2 pi, 2 pi if necessary, till I land in the interval minus pi to pi. And depending on whether I land to the right or the left, that determines this sign. So essentially what goes on here is that when you take a discrete time sinusoid and put it through an ideal D to C, no matter what TS is, to figure out what comes out first, you figure out the spelling of this signal. Like I like to think of these discrete time aliases, they're the same signal, different spellings. The spelling of the signal where the omega hat thing lies in the magic interval. And then you do a straightforward substitution, like so, to figure out the f0, the cosine that comes out.
So if we have a Marvel DC crossover, is there anything we can say about y's relation to x? Or is
Well,
it
I mean,
a different signal?
there would be some retcon problems, you know, but you get over that. You can get past that. Okay. Any other questions? Yep.
So the way that Shannon Nyquist kind of fits into this is we're guaranteed to return the original input signal from, or YFT will be equal to XFT if and only if after that is relative.
If.
If.
Sometimes only if. Sometimes it's weird. You know, there's weird cases where everything cancels out just right. So that, but yeah.
So what would the only if statements be?
I don't know, actually. That's a good question. Like his question is the following. The way we stated the sampling theorem, it's a one-way thing. If you sample a cosine faster than its Nyquist rate, then when you put it through an ideal interpolator, you get the cosine back. Okay? So his question is, what is the only if side of that? You know, that question. Like, you know, is there some way I can say that I must have sampled it faster than Nyquist rate if this happens? And I don't really know a good one of those. So I'll reserve judgment on that one. Yep, Jade.
So like if we have like a sum of sines or cosines, right, we find like the fundamental frequency that we have the greatest like common integer.
GCID of the, yeah.
But what happens if the frequencies aren't necessarily integers?
If those frequencies aren't, well, they don't have to be integers. When I say integer divisor, I don't mean a divisor that is an integer. I mean that over an integer. Like say you had, how about the frequencies are say 3/2 and say 7/3, right? What is the greatest common integer divisor of those? Yeah, that's 1, right? No, it's something else. It's like, how do you figure out greatest common integer divisors? You write down all the divisors in a row, right? And I usually do this with periods instead of frequencies. So I find lowest common integer multiple. So let's see. 3/2, that over 2 is 3/4, that over 3 is 1/2, that over 4 is 3/8, that over 5 is 3/10, that over 6 is 3/12. That's 1/4. So I need 7/3. That over 2 is 7/6. That over 3 is 7/9. Eventually, you're going to get the same thing here, okay? And that's going to be, no, that's the lowest. No, it's the greatest, yeah, because you're dividing. So anyway, these lists are going to have something in common after a while, as long as the ratio of those two things is a rational number. Okay. I think it's going to be, let's do it with periods instead. So then I'm finding, so I have 2/3, and eventually I'm going to get 2 on that list, right? Then I have 3/7, and eventually I'm going to get to 3 on that list. And now, eventually I'm going to get 6, and that's going to be it. So I think 1/6 is going to be the answer here. Could you do GCIDs in your head?
For easy fractions, like certainly if we start getting irrational frequencies, I mean, it's
No, let's not be irrational. Let's. Yeah.
I mean, for anything that you're going to test, I could probably just do that in my head.
Cool. So just wish you had his like savant qualities.
Is it safe to say you could just multiply by something to make them both integers, find a GCID, and then divide by that same number?
I think so.
Because like in this case, you just multiply by 6, you'd find probably the GCID is 1, and it's 1/6.
Yeah, I think that's a good way to do it. Yeah. Is that good? Is that okay?
Will we have calculators?
No calculators. So wait. So what's your name?
I'm George.
George. Okay. I thought that I've been looking at the pictures because I'm trying to practice up for this empty room thing, and I thought, oh, that must be George because you emailed me the other day about advisors, and so.
My idea makes me look like an egg, so probably I'll identify.
Well, that I had to decipher it a little bit, but no, ID pictures are not the greatest usually, so. But no calculators. We did it last. I don't think you'll need them. No, you will not need them. That I can say with confidence. Oh, finding polar form of a complex number? I'm not going to expect you to do any hard ones, but like like e to the j theta equals cosine theta plus j sine of theta? Well, that's what you have your 8.5 by 11 sheet for, right? You know, the ones you don't know. Now, this is what I've always wanted to do, is tell the class, you know, you can bring one 8.5 by 11 sheet of notes with you, both sides. And then when you get there, say, I told you could bring it. I didn't say you could use it, right? So put it away. Because the exercise. No,
I feel like you would have students just storm out.
Storm out? Maybe that's what the university should do. So get all you guys to go away. Okay, Alex, do you have a question?
Yeah, just a comment. So if there are any such like trig identities, they are going to be like theoretically you can construct really esoteric values of sine and cosine, but they're going to be easy ones like looks like pi over 3, pi over 4, or maybe like one step past.
Yeah, pi over 4 is a good one to know. Pi over 3 is a good one to know. Like you saw on.
Cosine and sine of your hand.
I never learned that.
Like this is the x-axis, this is the y-axis.
Oh.
Cosine of pi over 6 is.
I never learned that mnemonic.
3 over 2.
Excellent.
Just root 3 over 2, and then the sine is 1/2, and then this one's just root 2 over 2, root 2 over 2. Yeah.
So if I see people doing this during the test, I'll know.
Well, if you see me doing it.
Well, I
don't know if anyone else does.
I remember when I was a TA in grad school and we were doing cross products in the lineage and multivariable class. Like I was at the board and saying, well, you figure out how this goes by doing the right-hand rule. So I was writing on the board and I kept getting the wrong answer and I realized I was doing the right-hand rule with my non-writing hand. So that's where.
You gotta curl away.
Right.
Open your hand.
Okay, any other questions? Yeah. Not a dumb question, no.
No such thing.
Oh, yeah. Prelim is in Phillips 101. Didn't you guys, does everybody know that? Just tell your
7:30.
7:30, yes. And you get, it's the length of a class, so it's going to be an hour and 15. So.
Not an hour 30.
No. We have a question. Do I have any idea of how we're going to handle that? Okay. I do have an idea, but I haven't figured it out yet because this is all in such a state of flux. But what I'm thinking is, first of all, they have to be gradable. Okay, so they might be more short answer intensive than otherwise. But what I'm thinking of doing is devising a way for people to do a time-limited test, open book, because I can't really expect you to have closed books like wherever you are. A time-limited test by, when you access it, it gets recorded, and when you turn it in, it gets recorded. And so you have like an hour and 15 minutes or 2.5 hours, between those. And do it anytime you want. So not everyone in the world is doing it at the same time. So those of you who are in Singapore can do it on your time zone, and those of you who are in Homedale can do it in your time zone, right? Okay. Or even exit 172, so to speak. Hang on, just what was the question?
Doing math questions like this online.
We have to figure that out. See, that's another thing. Yeah.
Could you maybe do it so that you could write it out and then submit it and give us an additional 5 minutes to submit?
Yeah, these are all good suggestions, and that's why I put up that Canvas discussion. I don't know how those work. Are those I heard students sort of talking in the hall one day, like yesterday, saying, "Well, who wants a Canvas discussion?" And I'm like, "Oh my God, I just put one up." And it's like, they weren't people in this class; they were others. And I thought, "Oh, is this like a?"
Well, your name is tied to it. It's like Piazza but without anonymous.
Piazza but without anonymous?
Yeah. You can just
Can't I make it so that you can submit anonymously? I don't know.
Add a post on Piazza on whichever you can.
A pin a post so that, yeah, that's one way to do it. That's a good way to do it, yeah. Yeah, so we're open to suggestions. We're like, because this is, like I said, it's uncharted territory, and we're all learning. We're gonna, you know, so next fall when they say, oh, it's flu season, we're shutting down, you know, we'll know what to do. Okay, yeah. Put that up as a suggestion. Yeah.
That's what Molnar is doing.
It's what Molnar's doing?
Yeah.
Robin's doing that as well. I think
Yeah.
they both are planning on pitching in together on a document camp.
Okay.
So I think they're going to raise they want the department to pay for that.
Well, there's a document cam in Phillips 101.
Yeah,
Oh, there's one here as well. I mean, if they don't lock me out of this room. But see, the thing is that Blackboard is so much a part of my delivery system. I don't know. We'll see. We'll see what happens. We'll figure it out. Okay, so I'll see most of you tonight. Oh, and but one other. No, here. Yeah, there are a couple of people who are, for reasons unknown or known to me, are taking it not tonight but afterwards. So please don't talk about the test until after next Monday.